Good morning, everyone. Good. Yeah, we will continue today with supply chain analytics. So we should finish it today. And you will use your computers as we did last time. So there will be many exercises that we will do together. And we will cover many types of supply chain problems. Okay. So supply chain design problems, we'll do it right now. Also supply chain execution problems and supply chain people process problems. Good. Yeah, very important, and I would like to remind you this, that there are many studies showing that companies that use supply chain analytics, meaning that those companies that use data in order to solve problems, they happen to be more innovative than other companies, right? And also show that companies that make supply chain analytics innovate at the end, they have a higher supply chain performance. And therefore, analytics and innovation are very, very related to each other. We saw last week some strategic aspects with respect to supply chain analytics, how to use the data, let's say to decide whether to quote a tighter delivery window to customers. And we saw that the service level deriving from that higher delivery window, or from that actually shorter delivery window, which denotes more responsiveness, in order for the company at the end to implement it and to put it as a service to the customers, they have to improve their delivery processes, or to reduce, to shorten their processes. So, and this will lead, of course, to a supply chain innovation project. Also, we have seen with the NPV method, net present value method, how to calculate whether a supply chain innovation project is beneficial, is advantageous for the company or not. So we will continue today with other problems, supply chain design problems. By the way, we will some techniques and some problems. Yeah, we will do them, of course, not for large supply chains. We will do them for small supply chains, but they are actually extendable to larger supply chains. Okay, because if we will have a large supply chain, we can, of course, try to solve it, but it will take long time, right? So, but once you understood the principle, you can solve any problem that is similar to the problems that we will do. Yeah, especially here, the supply chain design, and also the network optimization problems, which are actually transportation problems. Okay, good. So, yeah, I tried to make an introduction in order to, I know that some students come a bit later, so that when we start with the simulation, we will have most of the students here in the class. Okay, so let's start with the supply chain design problem. So the problem looks like this. You are hired as a grocery chain analyst to determine how many truck docks should be constructed in a new regional distribution center. Okay? So, yeah, it may be a cross dock or whatever, but we would like to understand or to determine how many truck docks should be constructed. And we will use here the simulation technique in order to determine the number of docks. Who has already used Excel to make simulations? Yeah? Somebody else? No? Never? So Excel, yeah, is really, although it's a general purpose software, you find it in MS Office, but it is really powerful and it can do a lot of things. And we will see how we can do a simulation with Excel. Okay, so here we have the problem. So there are quite a lot of data here that we should dedicate some attention to. So a new regional distribution will be exclusively serviced by road trucks. So we will have only road trucks. The trucks will arrive in a random pattern of arrivals and will be unloaded on a first come, first to be unloaded sequence. So you have docks. Okay, yeah, so you have you have many docks. And then, I mean, this is the number that, or the optimal number that we will try to determine. So if you have let's say a cross dock or a distribution center, whatever, you have here, this is the center, and then you have docks here. Okay, so these are the entries. The entries to the distribution center. So there will be either the trucks, okay, coming, and they will be unloaded. And then we would like, so our task is to determine how many docks we should have here in order to have an optimal unloading, and we will see the variables that are required. Of course, when you have such a center with many docks, it will be, or let's say a center with 10 docks, it will be more costly than one with only 2 docks. So we will have only 2 entries in order to unload the goods, right? So and then the goods perhaps they will be distributed and afterwards. Yeah, there may be also other docks here, but this is not what we are interested in. Okay. Then we have, and then they will be first in, first served. Okay, first in, first served. Yeah. So this is the rule that we will use. It could be also called first in, first out, first in, first served. No problems. Then the truck cargo size and type will vary, and thus give rise to variable unloading rates. You see? So we don't know. Perhaps this is a big truck, big one, big truck. This is a small truck. So they will have different times for unloading. So this will, of course, need more time for unloading than the smaller one. But we don't know. We don't know whether we will have a big one or a small one. So we will see how to deal with that. Then trucks are not unloaded during their, so trucks that are not unloaded during their hour of arrival must wait for the next or subsequent hours to be unloaded. So it means that, yeah, you have all the 4 docks here that are busy, and then you have other trucks that are waiting. Okay? So if they are waiting, of course, they will not be served. So they will not serve in the hour where they came. Let's say they came between 8 and 9, but still there is work going on here. So perhaps they will be served in the hour after or the hour after. The only thing is that when you have a truck that is waiting, of course there will be some penalties. Okay, so you have to pay some money for the shipper, perhaps because you are letting the trucks waiting. So the predicted truck arrival is 3 trucks per hour. So this is on average. Okay, so we have average. So how to calculate the average? So it will be past data, perhaps other distribution centers, whatever. So you get the average. Average is equal to 3 trucks per hour. Now, we go on. So I try to make it a bit visual because there are a lot of data here. The average truck unloading duration will be 45 minutes, giving an average unloading rate of 1.33 trucks per hour. So for the average unloading, so we have the average duration is 45 minutes. So this is very important, this average arrival, okay? And here, duration unloading. You see, there are two different distributions. Actually, in terms of probability, there is a distribution for the arrivals of the trucks. So this is an uncertain process, a stochastic process. But you have also uncertainty in the unloading. So because the unloading depends on how big is the truck and how many goods are loaded on the truck. So the duration of the unloading is on average is 45 minutes. Meaning that we can unload, so we have an unloading rate of 1.33 trucks per hour. The construction costs per dock are 365,000, so per one single dock. And marginal truck waiting time cost is estimated at $47 per hour. So for having one dock, so you have to pay 365,000. So having two. So this is the data that we have. It could be other formula, but it is not very important here because we could manage very easily. And we have the cost of a delay of waiting time. So if this truck is waiting 1 hour, so we have to pay that truck $47 for having waited. Yeah, it's completely fair. It's totally fair. So you have a truck coming from a shipper that is just waiting and you don't serve it. So there will be penalties. Then, given the objective of minimizing overhead costs, what is the optimal number of docks for this new distribution center? You see, so we have a lot of data. Okay, so how could we use all of this data in order to determine the number of trucks? So if you try to make it via calculation, you will not solve anything. So you cannot solve the problem analytically. Analytically, it means that you will have one optimal solution. Okay, this is the number of trucks, the number of docks that minimize the total cost. Okay, so what are our costs actually? What are the costs that we should somehow confront together in order to solve the problem? What are the costs? We have two types of costs. So exactly. So the docks. So we have the costs of the docks. Cost of delay. Yeah. Gosh. Okay, the more docks we have in the distribution center, the less the waiting cost. The less docks we have, the higher the waiting costs. Okay, so having this problem, what do you think now? What is the data that is missing? So there is some data missing. I told you about it before. Exactly. You would say also the same thing. So we don't know the distribution of the arrivals, and we don't know the probability distribution of the unloading, right? Unloading capacities. So this is something, we cannot control. Okay? So we need this distribution. So first of all, we need this probability distributions. Arrivals and the unload capacity, or unloading capacity. Okay, now more or less we are aware of everything. We need, of course, the distribution center, the probability distributions. Now, okay, the next step is you decide to use Excel. Because it would best suit this task, whereby random numbers are used to generate the arrival and unloading distribution. What is a random number? Very important. What is a random number? When I tell you, for example, a random number between 0 and 1, what is a random number? What is the definition of random number? So we need a random number, because simulations, by the way, is based on random numbers. So if they are not random, the numbers, so you will have a biased distribution, and biased distribution, you cannot use it for simulation. So we have a random number here, random number. Random number between 0 and 1. It means a number that has equal probability as any other number between 0 and 1 to be taken. So you can take 0.1, you can take 0.15, you can take 0.20, you can take 0.25, 6, 7, 8, you can take 0.3912. So all of these numbers inside this table have all the same probabilities to be taken. So this is, what does it mean, a random number, right? No, it should be like this. But we will define the distribution in a way that, yeah, we will define it, yeah. Of course. So, but random number between 0 and 1 means that, or random numbers, it means that all these numbers between 0 and 1 have the same probability to be taken. Now, of course, the probability distribution, so when you take the normal distribution, right? The normal distribution, which is, yeah, not well drawn, okay? So you will have here, I'll try to improve it. Of course, the numbers here, they will have higher probabilities, or to have a number inside that interval, it will have higher probability, right? To be taken. Why? Because this is our distribution. And here we will define also our distribution. And the distribution based on data from, so data is collected in order to understand the arrival patterns of the organization's existing loading docks and the performance of its distribution center. So the truck arrival probabilities are this one. So these are the probabilities. So this is the distribution, right? The distribution of truck arrivals. Look, the numbers that we have are like this. So you have 10% probability, 10% probability in order to get, so 10% probability that we get no arrivals, no trucks. So in 1 hour, there is 10% probability that we will have no trucks arriving. Then we have 15% that we have so 15%, this is the probability, that we have one single truck arriving. Then we have 0.2, which is 20% that we have, so don't look at this, okay? Just look at the first column and the last one. So we have 20% probability that we get 2 trucks during 1 single hour, and then we have 12% that we get 5 trucks. So this is data from the past. And it is very, very simple to calculate it, right? You can look at the number of the hours, and then you see, okay, what is the probabilities or the percentages of having no truck, what is the probability of having yeah, 2 trucks, 3 trucks, so based on a lot of data from the past. So, and this is very important. If you don't capture the data, you cannot have the probability distribution. So in some way, you have to capture that data before. Otherwise, you have to make assumptions. And assumptions are problematic. And therefore, data analytics in general is based on data that you have already captured. So if you don't have a certain system inside the organization capturing the data somewhere, you cannot do it. So if you are doing it for the first time, you have to make assumptions, okay? Depending on other, on invoices, on past purchases, whatever, okay? Is it clear so far? Now, look, and then we would like now to identify intervals. So what Excel can do for us, and I can tell you, Excel can give us, I can use the function equal rand, and then parentheses. And this function in Excel gives me a random number between 0 and 1. So a number that has equal probability as every other number between 0 and 1 to be taken. Now, I have to consider these probabilities. I would like to have numbers in a way to consider these probabilities. Now, look, if I choose an interval, this one, between 0 and 0.1, what do you think? And here we find very important the definition that the random number is a number that has an equal probability as any other number to be taken. Now, if I take an interval of 0.1, what is the probability of having a number, a random number, inside that interval? It's 10%. Right? So it is a random number. All numbers have the same probability to be taken. And then I choose an interval inside this 0 to 1, which is 10%. So you have 10% probability of having a number here. Now, if I take 0.15, so yeah, I don't give here a lot of attention to the extreme values, and it's okay, by the way. I would like here to go to 0.25. So here the interval is 0.15. Okay. So what is the probability of having a random number between 0.1 and 0.15? Sorry, 0.25. So this is equal to 0.15. So the probability of having a number between 0.1 and 0.25 is 15%. So what I'm doing here by using the random number function of Excel and by using these intervals, actually I'm creating my probability distribution, right? Okay, is it clear? Any questions on this? Ask the question, because this is an important step in the whole thing. So I'm trying to translate these probabilities into a distribution that Excel can handle, because otherwise I cannot do that. So I'm telling Excel, and this is what I will do. Create a number between 0 and 1, random. Excel will say 0.26. Now, give me just 0 to 26. And then what I should do is that it is 0 to 26. I will look where 0.26 is. So 0.26 is here. So from 0.26 to 0.2045, this corresponds to Trump parameters equal to 2. It means that I have I can extend now, give me another random number, 0.85. okay? Jumps to 0.85. And then I will tell Excel, look at the interval. 0.85 corresponds to what truck arrivals, and it corresponds to 4. So what I'm doing here is I'm doing two things. The first thing is that I'm respecting my probabilities by defining this interval. And second, I'm giving a random number to Excel that is created also by Excel, and it will return to me the truck arrival number. Okay? Does it make sense? So I can see 80%, but not 100%. Any questions before we go? Okay. And then we have the unlimited probabilities. So we said we have the arrivals. And then we have to deal also with the unloading capacities. So, and here we have also data about unloading rates with 2 docks, unloading rates with 3 docks, and unloading rates with 4 docks. You can see here, look, the probability of having 5 trucks unloaded in 1 single hour when we have 2 docks only, it is 0%. Okay? It's 0. And then when we have 3 docks, the probability of having 5 trucks unloaded is 5%. However, when we have 4 docks, the probability of having 5 trucks unloaded is 0 to 45. And we take, of course, into account this 0 to 45 as well as all the probabilities by identifying the interval. So if the probability is low, the interval will be low. If the probability is high, the interval will be correspondingly bigger. Right? So this is the whole idea. Okay, so these are the numbers. So we need them. So this is the probability distribution of unloading capacities depending on the number of docks. So far, so good? So let's go and do some practice. Let's go to the Excel, and we will see how it functions. So how we will do the simulation. Stop sharing for a second. So you open the third Excel, which is Grocery Supply Chain Design Simulation. Okay, I will share again. Okay, you see. Look, I will do it for the 3 docks. It is the same thing when we do it for the second dock. Oh, sorry, for 2 docks. For distribution center with 4 docks. You can do it as an exercise at home, but it is the same mechanics. We will just do it for 2 docks. Sorry, for 3 docks. Now, you see here, at the very left, what I have the arrivals. It needs a bit of time. Yeah. So I have the arrivals. This is given. I have the unloading probability. So this is about the capacities that I have, or the unloading capacity. So it will give me the unloading capacities. So the capacities, it means the maximum number of trucks that can be unloaded in and out. This is my capacity. If I have, let's say, so the table gives me, by choosing a random number, I have at that time 4 trucks could be unloaded. It means my capacity is 4 trucks. I cannot unload more than 4 trucks. And if I have an arrival of 5, then you have an arrival of 5, yeah, even though it's 12% probability, but still you can have it 5 arrivals. On the other hand, you have just capacity for 4 to unload the trucks. Then, of course, there will be a delay of 1. Okay. If you have capacity of 4 and then you have only 2 arrivals, let's say, yeah, you will have 2 that, yeah, you don't use and that out. Okay, so 2 capacity, 2 truck capacity that you don't use. Good. Now, first of all, what should we do? What do you think? What should we do? First thing. Any ideas? To do the simulation, what is the first thing? Exactly. So in the first 2 columns, we have random number for arrivals and random number for unloads. And first of all, we have to create random numbers. I'll go to the here, and then I will create random numbers. I will write rand equal. No, I have to change it here to equal to random with 2 parentheses. Can you see? It's small. It's small. This is the problem always. You see? Excel created for me a random number between 0 and 1. You write. You can do it at the same time. Have you done it already? Equal to rand 2 parentheses, and then you create. And then, of course, how many numbers I would like to create? How many numbers? 24, because I will be looking for one day. Okay? So, what I will do is that I will just so the problem is when you do something in Excel, you will see that these numbers will always change. They keep changing. They keep changing. Whatever you do is small operation in Excel, they keep changing. So, but once we use them for simulation, they should be fixed. And then we should insert them as values inside the table in which we will do the simulation. So, look, I will. So you can see the first number before it was 0.9, right? Now it is 0.59. And then when I will copy that. I will go to the exercise, and then for the random number of arrivals, I will be entering them as values. So this is it. 1, 2, 3. When you it changed in the meantime, but now when I enter them as values, they will not change anymore. I can insert them once again as values. And then these numbers, they will be the same for the entire simulation. So they are random numbers, so it does not matter if I have 0.9 when I create them, and then when I insert them, there are other numbers. It doesn't matter. They are random numbers, okay? And the same, but during one single simulation, they should stay the same. So it is not good that when I'm doing my work on the simulation that they keep changing. So we should not have that situation. Are you so far okay with the insertion of the random numbers? You do it like this. You go here, and then there are many. So right-hand side of, and then you have 1, 2, 3 here, and you insert them as values. And this way they will not change. They must be. Yes, they must be. So there is no reason that they are equal. They must be different. But actually, these random numbers, they don't help me much. What I need the number of arrivals, and I need the number of capacity of truck unloading capacities, right? So I cannot work with them at these moments. What should I do? But I have the two tables, right? So what I can do is that I can in Excel. First of all, you have to look at one number. So for example, the first one is 0.70 here. You have completely different numbers in your table. And the results that we will find are completely different from the ones I have here. This should be clear. So 0.70, this is the first number. So how many, so this is the random number for arrivals. To how many concrete arrivals this corresponds? 0.70. 74, etc. 4, exactly. It's actually 70, no, it is, yeah, 3 or 4. So it will be, or yeah, let's take, so Excel will manage that. 0.60, right? 0.60. What is the number of arrivals that correspond to 0.60? 3, exactly. So I have to tell Excel, look at this column, enter the number, then go to that table, read where this number is located in which interval, and based on that interval, give me back the number of arrivals. Which function could help us with this? Read the number, go to the interval, or to the table, look where the number is located, in which interval, and give me back the number of arrivals. No. Exactly. Who said VLOOKUP? Yeah, very good. It is VLOOKUP. So it is VLOOKUP. So we are looking up a value here in a table, and then we are returning back the number that we are looking for. It is equal to VLOOKUP, and then we will see which inputs VLOOKUP function needs. Okay, so I'm using the VLOOKUP here, and I think my Excel does well with this, but I will test it out. Okay, now the number of arrivals, I will do it step by step. So I'm writing down VLOOKUP, so this is the function, right? So I'm looking for the number of arrivals. Should I make it bigger? Yeah. I will try. Because also I need Is it okay like this? Is it better? So V loop up. This is the number of arrivals. I will tell Excel, so this is lookup value. I would like to tell Excel, you should go to J16, J16, right? Read the value of J16, and then go to the table, and this is the table of arrivals. It has 3 columns. So I'm selecting that table. That will come, yes, exactly. And then from B3 to D8, from B3 to D8, okay? What is important here is to fix it, because that table do not, because I have to pull down, so I have to fix it with the dollar symbols. When I'm using the dollar symbols, so it will be, when I'm putting down afterwards, it will not change. So I'm putting here dollar B, $3, D, $8, and then I have to tell also Excel, I have to get a number back. And then the table actually is composed of 3 columns. So first, which is lower, the column lower, then second is the column up, and then arrivals is the column 3. And then I will tell Excel, give me the value inside the column 3, and therefore I will be putting 3 here. Okay? So, and here Excel gives me 3. Because it starts for 4 from 071, and 070 is 07, you can put whatever you want afterwards. So it starts from 071 for 4. So Excel is managing this very clearly and very good. Now, in order to get I told you that I have to pull down, so I do not care about the fact that the table will pull down also on the left-hand side. There will be no problems because it is already fixed. And then I just pull down, and then Excel will do this very automatically to me. Did you achieve that step? Okay. I'll do also the same with the unloading capacities. So I have here unload capacities. I'll do exactly the same thing. VLOOKUP. But here I have to use this value, which is the random number for unloads. Okay. Then I will use this table because this is the unloading probabilities table. Again, I have to be very careful. I have to say to Excel, do not change rows when I pull down later on. So I'm inserting the dollar symbols. And then I'm telling Excel again, I need the value in the third column. Lower is first, upper is second, trucks unloaded is third. And Excel, okay, for 0161, obviously it is 2, and it is right. And then I'm pulling down. Did you arrive at that step? Yes? Great. Yeah, you finished everything. Hmm? Good, we will see. Did you put the equations also inside? Yeah. Okay. Now we have to. Did you find everything? Who is still struggling? Okay, we need a bit of space here to write down the equations because we need to calculate the delays at the end because the delays are very important because of this optimization. Okay, first I'll go step by step because this is extremely relevant. So at the beginning we have 3 arrivals, right? How many trucks will be unloaded then? So the ones to be unloaded. Yeah, there are 3, so it will be equal to this. Okay. Now, what is the actually unloaded? The actually unloaded. I would say at our end, right, is equal to the actually unloaded. Very good. So in both at the same hour, right? Both at our end, right? Same hour. So very good. So the actually unloaded, it is the minimum of the unload capacity. So if I have a load capacity equal to 3 and to be unloaded is 5. So I have more than I can handle. So still I can be unloading only 3. If I have, let's say, here 4 unload capacity and 2 to be unloaded, I can unload only 2. Of course, I have capacities for more, but since there are only 2, I will be unloading 2. So this is the minimum of to be unloaded and unload capacity. Okay, so and the delayed is equal to, what is the delayed? Is equal to be unloaded minus the actually unloaded.
The other way.
But to be unloaded is always bigger than the actually unloaded. Actually unloaded is the minimum. Is the minimum. So to be unloaded is always bigger as actually unloaded. But to be unloaded is always bigger at the actually unloaded. So it is equal to be unloaded minus the actually unloaded. And we have 1 here. We have to unload for the first one. We have to unload 3, but we have an unload capacity of 2. Then we have 1 delay that hour. Okay, I will write it down here. Delay So at our n is equal to be unloaded minus actually unloaded. You see? To be unloaded is always bigger than actually unloaded. So this will be always positive number. Now I have to be, so I'm not putting anything now. I have to be a bit careful about the calculation of the next cell in the to be unloaded. How does it, so the to be unloaded is equal to be unloaded at our is equal to, of course, the arrivals at our n plus exactly delayed from our n minus 1. And we have to take this into account for the next cell because the delays start from the second hour. Okay, at the first hour we start without delays. Okay, so it is equal to, so to be unloaded to the arrivals, which is N7 here, sorry, N17, plus the delays from the hour before, which is here M16, which is equal to 1. I'm making it bigger here. So that so what I'm doing now, I have all the formulas. What I should do is that I will just pull down because everything should be okay. And then I have at the end, okay, the delays. The formula is already there. I have here already the sum. Yeah, I should say I have a better case here in my simulation. I have only 8 hours of delay in sum because for 8 hours, $47 per hour. How many hours of delay do you have? It changes. There are problems in the formulas. Okay. Okay. How many? 55. Wow. Yeah, it was really a bad case. Yeah. Okay. Yeah, we have 55 here. 63. Wow. 63. Yeah. I don't know. I'm very lucky here. Yeah. How many delays? You are still calculating? Calculating? How many? No? Yeah, I'm still calculating. Problems with the formulas? Yeah, 63, 56, 55. So I can wait a bit until you find the numbers. I know for the first time it could be a bit challenging. I know, therefore I wanted to go step by step. Because any small mistake, it could destroy your simulation, right? Okay, just to tell you something here. Would you rely on the results just after one single run of simulation? No. This is very important when you are doing simulations. Do not rely on one single run. I would say here you should simulate perhaps 1 month, 30 days, and then calculate the average. Because here, after my simulation, I have only 8 hours of delay. You have more than 60, you have 55 here. So this is obviously a lot of discrepancies. So we have to rerun the simulation at least, I would say, for 1 month. You can rerun it for 1 year if you want. Of course, you can do that. But do not rely on only one single run of simulation. This is extremely important. Yeah, I would like really to hear me that, because if you go afterwards to practice to the company and then you are building your simulation on only one run because you say the professor has told, no, I didn't tell you that. No, I told you, please do many runs, as many runs as you can for your simulation. Okay? We have everything, and you will see on the slides we have completely different results. But this is because of the random numbers. I cannot do anything for that. Okay, I will just reshare the slides. Okay, here you have a couple of indications. So all what we have done, so that when you go back home and you would like to rework the exercise, so you have all the indications. So the VLOOKUP function, the equations. So all the equations here that we used, you have them. Also, I will upload this doc at the end of the lecture. Then, yeah, as you can see here, it is a simulation run with 2 docs. So one 24-hour simulation for the 2 dock case. 66 trucks arrived over the 24 hours, but only 50 were unloaded. There has been 128 truck hours of delays. It means that some trucks, perhaps they had to wait for 1 hour. So they are not the next hour. They have even not been served the hour after, but the hour after, and of course for every hour there will be $47 of delay penalties. And you have here the numbers, right? So it is a 2 dock situation. Yeah, this simulation has been run here also for 3 and 4 docks. Of course, when we increase the number of docks, the delayed trucks here, we have 45. Still, we did not reach 60, but it's great, 60. Yeah, I do not remember that I reached it once by simulating this, but very good. 17 for the 4 docks here. So as I told you, this is only one single run. We should do it more, and then we take the average numbers. But yeah, we don't do it here because otherwise it would be very long. So what I will do here is that let's imagine these numbers. So the numbers here for the 2 docks, and the numbers here for 3 docks and 4 docks. They have been obtained after doing or after having done many runs of the simulations. And let's take the analysis now. So this limited run results indicate an unloading shortfall. So for the 2 dock case of 16 trucks per day with a total 128 truck hour delays representing a cost of 120 hours multiplied with 47, it means that for one day here, for one day, we have $6,000 as delay costs, right? So delay cost for one day is 6,000. Now, with 3 docks, 58 of the 66 truck arrivals are unloaded with a total of 45 truck hours of delay. The delay cost of 3 docks is $2,000. For the 4 dock case, 64 out of 66 arrivals are unloaded with a total of 17 truck hours of delay, and the delay cost for 4 docks has reduced to $799 per day. Given these results, the analyst calculates the possible saving from adding a 3rd dock. So we start with 2 docks, and then we calculate the delays costs for 1 hour, and then we subtract this from the delays that are induced by the 3 docks, which is 2,115. It means that the difference in delays costs between 2 docks and 3 docks is 3,901. In other words, when I have 3 docks, I am saving per day $3,901. Okay, so per day saving is 3,901. Then adding a 4th dock, and then I compare the delay costs of 3 and 4 docks, which is 1,316 per day. So when I add a 4th dock, I am saving, as compared to a 3 docks situation, $1,316 per day. So now I can calculate the payback. Given the capital cost of each dock, which is $365,000, then the savings could pay back the cost of the 3rd dock in 94 days. How am I calculating this? I am dividing 365 with 3,901, so this is from 2 to 3. And then I find that I can actually pay back my additional dock in just 94 days, and the cost of the 4th dock in 277 days. How do I calculate 277? It is 365,000 divided by 1,316. You can do the calculation, and you can find the number of days after which you are paying back the additional dock. So according to this simulation, it is much better to go for a 4-dock distribution center. And this way, we are paying back actually the 4 docks just in 277 days, right? So it's extremely fast. So a dock will last for sure more than 1 year, perhaps for more than 10 years. And this way you would, perhaps you have to make simulations for 5, 6, 7, 8 docks. Of course, here we need the probability distributions, but this is actually what you can do in order to identify the optimal number of docks. Yes, please. This is sunk cost. So when you have it, when you, yeah, it is out there. So we do not calculate or we do not integrate the variable cost of people perhaps, but you can also do it. And then, of course, this will increase the complexity, but yeah, you can find some way out of it. Yeah, a simulation, of course, you can try to integrate whatever costs you want. The only thing is that do you have these costs and to which extent they are important? Okay, to which extent? Yeah, because look, when you are paying people for working at a distribution center, you will not vary the number of people every day or every hour. What you will do is that perhaps you will have people that get salaries and they will be working all the time. So it will be more or less a fixed cost. Whatever the number of arrivals is, whatever the number of undocking, these are the people there. If there is some work, they work. If not, they will not work. So, yeah, and this is something you should take into account. Right? But also it will perhaps not have a lot of influence. But one thing is sure, if you have 5 or 6 dogs, it's not like when you have 200 dogs. So you will need much more people, right, to work. Yeah, I hope you did the exercise correctly and then managed all the formulas. What about having a short break now? We can have a short break for, let's say, 15 minutes. So we continue at 9:52. Okay, we continue with the next supply chain analytics problem, and it is called the network optimization problem. Yeah, before starting, who has already had a course on management science or operations research? So, anyone else? Who used the simplex method in operations research course? Or today we will not learn how simplex works because yeah, I remember as I studied operations research, the professor has required perhaps 6 hours to explain how simplex works with all of the mechanics inside. But today we will not do this. Today we will see what kind of problems we can solve, or what the supply chain network optimization problem, and then this problem is a linear problem that can be solved very simply by using the simplex method. What is important for us is the modeling, how to put the exercise or the problem into a model that Excel can solve. Because in the meantime, we have a lot of solvers, among others, Excel, the Excel solver, that can help us with solving the linear program with really few efforts. But what you should do still is the modeling, and you should be able to do this. So we have here an RFID tag manufacturer. Just to write it down, simplex, this is the simplex method. It has been discovered many years ago, I think in the 40s, for solving linear programs. An RFID tag manufacturer based in Australia has currently an sufficient capacity to meet total demand and is looking to add a new manufacturing facility to its supply chain design. So you see the problem. Yeah, a company would like to extend its production capacities. The question is where to locate the new plant. manufacturer prefers to build its manufacturing facilities in regional areas due to lower land prices and more stable workforces. Two potential sites, so this example is Australian. So we have Australian cities here, have been identified, Casino and Goulburn in Australia. So the RFID tag manufacturer wants to know which of the two would minimize its cost base. Good. Of course, we need some data about this. So the company will not start from zero. The company has already production plans, but it would like to extend them. The company has already some markets, and it will serve these markets with the existing plans, of course, but it will add a new one. So we have some network data. Yeah, we have here three markets. They market in Sydney, Melbourne, and Brisbane. Yeah, and we have also the quantities that are required by each market, 25,000 from Sydney, Melbourne, 20,000, and Brisbane, 15,000. And we have two manufacturing plants, two capacities that are already there existing in Newcastle and Albury. And then there has been, capacity of 30,000 and 12,000. And then the company proposes to add a new plant, but they don't know when. They would like, perhaps they have two candidates, two potential areas, which are Casino and Goulburn. Good, we have here the data. So Newcastle, Albury, so these are the current manufacturing plants. They are delivering, of course, Sydney, Melbourne, Brisbane, each one, and also Casino, if it enters into production or Goulburn, they will be also serving the same markets. We have the manufacturing cost per unit for each of the manufacturing plants, and then we have also the transportation costs. So we have something like this. So we have here two plants, and we have three markets. Okay? So the first market is Sydney, Melbourne, and Brisbane. Okay. Sydney, Melbourne, and Brisbane. So these are the markets. And we have the manufacturing plants. They are situated in different cities, which are Newcastle and Albury. And then we propose to make the calculations once for Casino in order to see how the costs will be, and then one time also for Goulburn. Let's do it for Casino here. So this is the third plan. So third plan. Still to be constructed. Still, so it's a proposal, right? And then we have, of course, flows like this. So we call this one X1, X2, X3. From Albury, also the same thing. So this is X4, X5, X6. So this is the new one. So we calculate or make the optimization for this city at first, and then we can go for the other one, but we do it for one single city because it's basically the same thing. So to save some time, we do it only for this. And then we have X7, X8, and X9. So what are X's? The flows, it may concretely are the quantities. Yeah? So there will be X1 quantity going from Newcastle, so X1 units from Newcastle to Sydney, etc. So let's put this into equations. Let's put this into equations. Now, yeah, at least for, yeah, let's say for Newcastle, right? So for Newcastle, we have to Sydney, to Melbourne, to Brisbane. So the manufacturing cost per unit is staying the same because it is from Newcastle. Okay, you can see the difference between Newcastle and Albury. Albury has a manufacturing cost per unit equal to 80. And then, of course, the transportation costs, they are different because of the distances, of course, that we don't have, but we should trust here the exercise saying that the transport cost per unit from Newcastle to Sydney is equal to 18, making the total corridor cost equal to 100, right? So the quantity that is going, let's say, from, so this is the quantity that is produced by Newcastle, right? So this is the quantity produced. So this is the quantity produced. And then what this quantity produced verify actually? What is the constraint that should be verified for this? Exactly. So this should be lower than the capacity at the manufacturing plant of Newcastle, right? So it's, what is the capacity? The capacity at Newcastle is 30,000. So it should be smaller than 30,000. You can do the same also for Albury. It should be smaller than, you can help me, 20,000. And then for Casino, so this is what we will do at first. It is x7 plus x8. Right? Do you agree? Okay. What are the next constraints that we have that we should also satisfy? I'm starting with the constraints. I should have started with the objective function, what I would to do, but let's say here I'm starting with the constraints. Now, I have also some constraints on the market, right? I should satisfy the demands. So, what is coming into Sydney? Coming into Sydney, X1, X4, and X7. X1, so Sydney. So this is the first market I have. And here, what is the constraint? 2? Very good. It should be equal to 25,000. So this is the first constraint. I have to satisfy the demand at Sydney. Then I'm doing the same also for Melbourne. For Melbourne, I'm seeing also that it is x5 and x8. x2 plus x5 plus x8, you help me, is equal to 20,000. And then for Brisbane, x3 plus x6 plus x9 is equal to 15,000. Right? So these are my constraints. So I cannot produce more than my capacity, and I have to fulfill the market demand. So, and by the way, this is the model. This is what we are doing here, and this is the transportation problem. This is the modeling. Of course, I need the objective function. Objective function. Yeah, this is what is called in operational research. The objective function is the function that I would like to optimize, either to minimize or to maximize the objective function. So am I here in front of a minimization or maximization problem? Minimization. Why? Because it is about cost. So I'm minimizing cost. So minimizing the total cost. Right? So what is the total cost? Minimizing of what? Actually, I have to look at the tables. So 1 unit produced by Newcastle and transported to Sydney is 100. So I'm minimizing 100 x1 plus then from Newcastle to Melbourne. From Newcastle to Melbourne, 115 plus 115 x2 plus from Newcastle to Sydney. And this is x, no, to Brisbane, sorry. And it is 105. It's 3 plus. Yeah, I'm doing it here. Now I can do it. Yeah, you can help me. 100. Who would like to help me? Yeah, because otherwise, always I have to come back and sit. X4. Sorry, what? 96 x7. Thank you, excellent. So, and this is our objective function. So we have to maximize this. So what we have done is that we translated this data into a model. And this is the linear model because the objective function is linear. You see, this is linear, right? This is linear. So we don't have squared, nothing. Yeah, everything is fine. And also the constraints, they are linear. Of course, here I have to, in the constraints, I should not forget about something. That, yes, more than 0 and not non-negative, but also there should be integers, right? So it's integers, yeah, positive or integers, right? Okay. So x1, x2, x3, they should be integers. This is also a constraint because I cannot define a unit equal to 35.6. So a unit is 35 or 36 or 37. It is not. They are not. They should not be. Yeah. They should be integers. No? Okay. Any question on this? Now what we can do is that we go to our Excel, and then we put everything into Excel, and Excel will solve this. think you have this also in your table, right? In the Excel sheet, you have this? Exactly this, okay. So, I have represented all the variables. So the solution, this is what we are looking for. So this is in yellow. So we have the costs. So these are the costs, 100, 150, 105, etc. Then we have the constraints. We have the Sydney's, we start with the demand. Yeah, then we have the sign here, but it's just for you. Then x1 plus x4 plus x7, etc., etc. And now we have to just put this into the solver of Excel, and Excel will solve it. Who has already the solver in Excel? Who has already used the solver? Okay, you use the solver. Those who didn't use the solver, you have to install it. Okay, and how do you install it? It's very easy. Hopefully it works very, very quickly. You go to File, then you go to Options, so File. Yeah, I have my Excel in English, so should go to this. And then Options, you click on Options. You have this. Okay, did you get into that? And then you have to go to Add-ins here, just before the last one, Trust Center, Add-ins. And you can see here that I have my solver, solver add-in is already there. But you have to look at the solver and you have to install it. So Excel does not provide you with the solver and already installed, but it is somehow hidden. In order to use it, you have to install it for one single time, and then once you install it, you will have it. Yeah, give me the signal when you have already done that, because we cannot come for, so if you don't have the solver, you cannot make the calculations. Yeah, you remember we said that supply chain innovation is also about structures. And supply chain design, what we're looking at here is about structure. So when we add a new plant, actually we are changing the structure of the supply chain. And then we have to be very careful which plant or which city we are actually selecting in order to serve our markets, and because we are changing the design of our supply chain, right? So it may not be called a radical innovation, but at least it's incremental. Good. Did you already install it? Who could not install it? So it can, by the way, it happens so that it is not installed and you have to struggle a bit with it. It can happen. So please try to solve it, because we will need it now and afterwards. So for this and for the problem afterwards. Already done here? You good? So you did it? Okay. I don't need to reinstall my solver. Believe me, sometimes when I would like to solve problems, sometimes I do not find the solver. And then I have to restart my computer, and all of a sudden when I restart, I find my solver. So this is not explicable. I don't know why, but sometimes it happens. I mean, hopefully not today, not during the lecture. Okay. Where I find it, I go to data. And then I see my solver. You see the solver here? You see? So it is there. I'm quite happy. Okay. But before that, I have to make a bit of arrangements on the table. I have to put some formulas in order to be able to use the solver. Okay, so what I'm going here, first of all, I have to insert my objective function. Not so the formulation of the function. So it's equal to, look, it is 100 multiplied with this, so these are just text. So it will be 100 multiplied with this, 115 multiplied with the cell just above, 105. So it is actually the sum product of this row, sum product of the first row. So yeah, it will come. Yes, now it is selected. And then, comma. And I will put then so what is this? So we have here 100 x1, 150 x2, etc. When I enter the row, so I'm using some product, and then I'm putting this row and then comma this row. Excel will do 100 x1 sum, so this is the product, first product, plus 115 plus x2, etc. So this is what Excel does when using this function sum product. Make sense? So instead of inserting it one by one, I'm putting the sum product, and then it will ease my life. Of course, when I'm pushing on enter, then it is 0 because there is nothing inside the yellow cells. And then I have to define my constraints, or to put the formulas for my constraints here. So could you tell me the formula about the Sidney's demand? So you see here, it is already well chosen. Very good. So I will use what I will do in order to do it very quickly. I will use some product of the solution row, but I will put the dollar symbols to fix it, and then I will pull down. And then I will define very quickly all the constraints. So it is the sum product again of this one. So this is the solutions row. Yeah, I go a bit slower so that, yeah, here, yes. But as I told you, I will put here the dollar symbols because I have to use it afterwards also for the definition of the other constraints. And then I will be doing this. I'll be selecting then the Sidney's demand row. So because I have, look, Sidney's demand row is x1 plus x4 plus x. So I put 1 for the x1, 0, 0 for x2 and x3 because they are not in the formula. And then for x4, I put 1. So when I'm making the sum product, I will receive directly x1 plus x4 plus x7. Because I put zeros in the cells which are related to x2, x3, x5, and x6, and x8 and x9. And because of this, I can use the sum product. And then I will enter. Yeah, and this is, yeah, very elegant because I don't have to insert the formulas again. I just pull down. Yeah, the solution is fixed. I get for all of the sum products, and then I have everything. I have identified, or I put the formulas here in Excel already for all my constraints. And then you have to go to data. You have to go to data. Data, and then solver. And when you click on solver, you will receive this. Did you have the solver? Yeah. Did you have this window already? So, do we have a minimization problem or a maximization problem? Obviously, we have a minimization problem, okay? So, this is minimization problem. So, we would like to minimize. So, I will click on minimizing. And then I would like to set the objective. So, the objective function, so this is my objective. I would like to minimize this. So, I click then here on set objective, and I will go to the cell where I inserted the formula, which is K3. K3. K3 is where I have a 0. K3, 1, 2, 3. So this is where I put the formula, this formula. Right? I put the formula there. Done? Ready? And then here, I have to tell Excel what are the variables that should change. I go, so it should be read like this. Minimize K3, which corresponds to the total costs, by changing the cells in the solution. I'm starting from B2 until J2. Excel, the solver will put them automatically when I just click on the cells. And then now, once I have done this, I have to add constraint by constraint, right? So minimize the total cost by changing the cells, and then under the constraints, and then I will be adding constraint by constraint. So I have to say to Excel that this is the left-hand side of the inequality, or of the equality. So K6 should be equal to M6. So I have to put change here, K6 equal to, and then the value here of M6, right? And then I'm adding that. Second constraint. I will be having K7 should be equal to M7. Add. Then K8 should be equal to M8. Does it function? Does it work? Or already done? Solve the problem? Okay. We're still struggling with inserting the data, the constraints? Okay, does it work? Yes. And we have to add then the next constraint, which should be smaller or equal to M9. I have to add K10, which should be smaller or equal to M10, and then I have to add the next constraint, which is K11, which should be smaller or equal to 12,500, which is equal to M11. And then I have to add the fact that these should be, all of these cells, B2 to J2, even if you don't do them in this case, it's not a problem, but I think it's better to do it, is equal to integer. So it is an integer, or integer, whatever you would like to call it, okay? And then I will be pressing on OK. And when I press on OK, I will have all of the constraints. Yeah, the overview of all constraints that I inserted. And then I will solve the problem. I will say to Excel, solve. Yeah, very important. It was already simplex RP. I'll come back to it once again. So I did not show this because it was already simplex in my solver. And then I have the solutions. So the solution will be x1 should be equal to 15 to 25,000, x3 equal to 2,500, etc. So this is the flows, the quantities that have to be transported from Newcastle, Albury, and Casino to the different markets. And then I have also the total cost. Right? You can see, for example, that x4 is equal to 0. What does it mean x4 is equal to 0? It means that no flows from Albury to Sydney. Keep it at 0. Do not do that. So it's not optimal to send or to ship from Albury to Sydney. Just to go back and to show you, look, yeah, here I was too fast because I saw it is simplex, but you could have used, yeah, it is simplex linear programming. This is what we have to use here. So you can use non-linear programming or evolutionary programming that we are not interested in here. So yeah, we keep this. Who found the solution already? Great, very good, great, excellent. So if you have not done it before, so it is, congratulations, it's your first time that you are using simplex and you use it for a supply chain design problem. So this is how the way it goes. And in practice, perhaps we will have much bigger problem. You have to get the data, of course, but it is this one. I tell you something that when you have a lot of data or a big problem, Excel could have some issues. And then you have to use some sophisticated solvers in order to solve the problem. Or use Python, perhaps, program this problem inside and then solve it. Okay? So I'll stop sharing here because we solved the problem. Now we go again to our slides. Okay, we have the network data. Okay, the first option, we said this is for a casino. We have, these are the numbers, the same that we found. I will not solve the problem for the next city, the second option, which is Goldberg. It's basically the same, only that we will change the values. And then you can see here that we have 5,965,000, and then for the other we have 5,790,000. So there is a difference which makes the first option better than the second option. And then based on this calculation, we will go then for the first option. So of course, after having solved the problem, comparison of the total monthly cost result of each scenario shows that the casino option is more favorable than the Goldberg option to the extent of 175,000 per month. So these are the monthly costs that we dealt with. because we have the monthly data with respect to demand and capacities, etc. And this will correspond to 2.1 million per year. So it's just multiplying with 12. This is a sizable difference and is large enough for a supply chain analyst to recommend to management that the casino site option is the preferred one from a cost minimization point of view. From a cost minimization point of view. Yeah, good. Any remark or comment on this? So what you can do, of course, if you feel a bit insecure, uncertain, you can do it 2, 3 times. You can change a bit the data, do it for the other city, etc. And then you will get a lot of comfort in doing this. But for me, what's most important, because sometimes, of course, you can do a small mistake in Excel, and you can spend the whole afternoon trying to discover which mistake you did. Yeah, this is sometimes like this. Yeah, what is important to me is that you do this work, right? So how to model, how to transform the problem into equations, right? And this is the modeling part. Okay. Now we will go to chain execution. Of course, if there are any questions, I will be happy to take them. Let's go to supply chain execution. And then what we will do a transshipment problem, which is very, very similar to what we have seen before, but you will see there are some differences which are extremely relevant that we have to take into account. And then we will do the theory of constraints. Perhaps you have seen it before, but I think this is an important supply chain analytics tool, but also it can be a trigger for supply chain innovations, as we will see afterwards. Okay, I will be erasing this because I need, again, the board. Okay, the shipment problem is similar to the transportation problem that we solved before, excepting the addition of transshipment points, which are regional distribution centers between the point of manufacture and the market. A company called Logfire makes low combustion heaters in Newcastle and Wollongong. These are then shipped to 2 distribution centers, Musselbrook and Queen Bain, so it's not very important. And from the distribution centers, the heaters are shipped as ordered to supply hubs. So the Logfire company would like to minimize the transportation costs with shipping enough heaters to meet demand levels in each final destination's city, with observing capacity constraints at their 2 manufacturing sites. Because Musselbrook and Queen Bain are transshipment points, the number of units shipped out of each of them must be equal to the number of units shipped into them. So we have 2 manufacturing plants, or they are a company that makes combustion heaters in Newcastle and Wollongong. So we have 2 cities. We call them 1 and 2. We're making the so these are plants, manufacturing plants. And then we have the transshipment points. So we call them 3 and 4. And then we have 3 markets, right? Albury, Dubois, and Armidale. So these are the distribution centers. The heaters are shipped as ordered to supply hubs. So these are the supply hubs. So this is 5, 6, and 7. Okay? And what we have flows like this. So we call it here x13. So from 1 to 3. And then we call this flow these are quantities x14. Then from 2 to 3, this is x to 3. And from 2 to 4, this is x to 4. And then we have from 3 to 5, so this is x3, 5, x3, 6, and x3, 7. And then we have x4, 5, x4, 6, and then x. So it's obviously very similar to the problem that we had before. The only thing is that we have a transshipment point. And we should take one thing into account is that at the transshipment, so first of all, we can write the constraints. Let's write the constraints. So capacity constraints. So could you tell me the capacity constraints? And one, whatever the name of the. Okay, I have to go perhaps. We don't have here the numbers. Okay. You can give me the numbers. Then x13 plus x14. Very good. Then the next constraint is 725. Okay, then we have the supply hubs. This is capacity supply hubs. X. We should 35. x35 plus x45 equal to the demand at 1, so it's 477. Right? And then x36 plus x46 equal to 365, right? X, then 3, 7 plus X squared 7 equal to 2, 55, 85. Okay, so we have so this is the market constraints. Let's say that we have the demand constraints. We have capacity constraints, but we have also other constraints. And we should put them here. Okay, I don't have place, and they are also a bit bigger. Could you tell me what are the next constraints that we have? The transshipment. The transshipment. So all what comes into 3 has to go out of 3. It means at the transshipment point, we have x13 plus x23 is equal to, or we can do it also like this. So we can have minus x35 plus x3 minus x35 minus x36 minus x37 equal to 0. And then we have x14 plus x24 minus x45 minus x46 minus x47. And of course the xi's, yeah, this x's, xigs, they should be so these are the constraints that we have. Okay? And we solved the problem exactly the same way that we have solved it before. You can see this is, yeah, we forgot about something, which is the objective function, right? So we should not forget about it. So we are minimizing cost. So we can, yeah, get the numbers here. So actually it is 3x13 plus 6x14. So these are the numbers. So this is we are not including here the manufacturing costs. We are just using the logistics costs for this problem. So it may be we can do it. We can just increase the manufacturing cost, but yeah, we're doing it this way in this case. Good. And then we have to solve our problem. So you can open your Excel. Okay, you will help me now with putting the constraints, with inserting the constraints. I have to put, first of all, a series of ones and zeros, right? In order to do the same technique as before. So, yeah, so the Newcastle capacitor, so Newcastle is the first one, x13, x14, and obviously x13 plus x14 is smaller than 875. So I have to put one here and one here, right? Because when I'm using the sum product afterwards, yeah, all of the other terms, they will be canceling out. Okay, could you help me with Wollongong capacity, which is 2, which is 32? Where should I put the ones? Very good. Then for Albury demand. So we are here x35, x45, right? And then for the fourth one, it will be x46, and then we did not do mistakes. I think it's just we are interpreting this. So whenever we have an x37, let's say when we have an x37, we have to look here, and for x37 here for the fifth one, which is the fifth constraint, we have to put one. And then for the transshipment points, it means Musselbrook empty and Queanbeyan transshipment point empty. What do we have? We have x13 plus x23. x13 plus x23, right? And then minus x35 minus x36 minus x37. I have to put here minus 1, then minus 1 here, minus 1 here. And then I have to put here the same thing for x14 plus x24, x1. I'm sorry. Did I make a mistake? Why? Because it is a sign, minus sign here. It should be minus, minus, minus. Because x13 plus x23, it should be equal to x35 plus x36 plus x37. I put all of them on the left-hand side, so there will be minuses. So 1 here plus x24, and then x45, x46, x47, minus 1, minus 1, minus 1. Did you get it already? And then I have to insert my formulas, okay? Because the solver can work with cells, not with formulas. So I have to insert the formulas already in the cells, and then I can go to my solver. Now, practically, I will be doing the same thing as I have done before. So I have here the units shipped. I can put them in color. I'm also will insert here the formula with the sum product of the units shipped multiplied with the shipping costs. And I will be also inserting formulas here. So I will use the same thing, the sum product. The shipping costs per unit, they are already there. So I will be selecting this row of the units shipped. So this is actually what I'm looking for, what I would like to solve for. And I will be multiplying this with the shipping cost per unit. Of course, I will get 0 at the moment. And then I will do the same thing with the sum product. I will be selecting this, and I should not forget, I should put the dollar sign here because they should not move when I'm pulling down. And I will select this. So from B13 until K13, it is obviously 0. And then I'm pulling down. So you can verify also here B10, K10, which it is always 10, but here, yeah, I am in 18, so everything is fine. What is next? Put solving it. So going to data, I have my solver there. First of all, it is a minimization problem. I have to select minimum. Then minimizing what? I have to minimize the cost in this formula, right? It is L11. L11, right? By changing the cells, it's very easy. This is the units shipped. I would like to know how many units to ship from one plant to the transshipment point, from the transshipment point then to the distribution points, etc. Then, of course, we will add our constraints, constraint by constraint. Yeah, by the way, we have to be very careful here. So you see here, I have GRG nonlinear. I'm not solving a nonlinear problem. I'm solving a linear problem with a simplex LP method. And then I will add my constraints. My constraints, I have here also the sign. I should be very careful. So I have 2 inequalities. The rest is equalities. The cell reference. This is this one. Then for the constraints. So I will do it a bit faster in the hope I'm not doing mistakes. So please, if I'm doing mistakes, you tell me. I should be equal here. And then L15. So I'm in the third one. Okay, the fourth one equal. The fourth one is 16. Then constraint 1, 2, 3, 4. This one, and the fifth one should be equal to the fifth one. I hope I did not make mistakes. Add this one equal to this one, and then I'm adding this constraint. It's not the last one. The last one, they should be integers. Add. Then I will select all of these, and I should impose that they are all integers. Yeah. Did I make mistakes? No. Okay. Hopefully not. Okay. So the solver will show me all of the constraints that I inserted, and then I will solve the problem. Okay. And now I have the solution. So I can see that x13 should be equal to 402. x14 it should be equal to 0. x23 should be equal to 0. x24 725, etc., etc. So this is the optimal solution, and then the costs when I optimize my flows, it will be equal to 7,492. Yes, please. I don't know. I don't know why. Hmm? Yeah. Yeah. Okay, I have solved it before, so I put the solution here, and also and I find the same that ones that I found here. So we did together. I don't know. We have the same. Yes, please. No, did you use simplex? Yes, they use simplex. You have to use simplex, the simplex method. Mm. There are more than one. Yeah, and then the minimum costs are the same.
Yes, I have you better family right the other.
You have 7,492 minimal cost. Yes?
Yes.
Yeah. Try it once again. Do you have the same minimal cost, but different? So you have to verify it if it is the same then. Yeah, very sure. I have been doing it a couple of times. I got always the same results, so I do not know what happened here. Yeah, I know. So if it's not a vertex, but you have it's not on an edge somehow. You have it's like when, yeah, in a curve, when you have more or less all of this region could be optimal, right? But I don't know for this specific number why you have some different results. But anyway, I know that this is the right result, and I have done most of the things are right. So not most of the things, all of the things I did are right. There's a big difference. Anyway, and then it is actually the same solution that I also have on the slides. Yeah, who else has found the results? No? Did you get it? Why? Why? So you have found, all of you, the same total cost but different one? I don't know why. Anyway, and it happens that you have found different results from the ones I found and the ones that should be, okay?
I do actually like the results. This solution we have now, the production capacity of Newcastle, one we have with one logo, but we produce one less units in Wollongong and one more in Newcastle, and and then to end these couple marks and then eight, just like one of the formula, for example, which is also eight.
Okay.
Per unit.
So you will have a more balanced use of capacities in this way. No, but because this is a problem. You have one that is 100% used. So if we look here at the results, so yeah, this capacity 725, the one of Wollongong is completely saturated. This one is not saturated. It's saturated as 402. And obviously this is a problem. So you have about half of the capacity is not used. So you may think of how to to saturate this capacity, because otherwise it is just waste of money and waste of investment, right? Anyway, please recalculate it again. Try to get the table, paste it on another Excel, and then recalculate. But do it at home. Because as I told you, I have done it a couple of times, and always obtained the same results. So I will stop here. And then we go to the results. Okay, so actually this is the same result I have here on the table, on the slide, that the one I found. Okay, the construction of the spreadsheet, I think we should not go into it because we know it exactly how it works. Okay, some indications here. I'm sorry. I was too fast. Yes. So, okay. So the results indicate a total transport cost of 7,492 per year for the supply chain configuration and data used for this problem. All demand was met. All of Wollongong's capacity was used, whereas only 46% of Newcastle's capacity was used. Of course, this is something we have to dig into more from a company's perspective. So the company's analyst recommends the route loading patterns determined, and also questions if demand, so this is the route, so the routes have been based on the optimization are recommended, but also recommends that, or questions if demand can sensibly be stimulated, so the demand here, in order to saturate, so if we can increase somehow the demand, so it could be a marketing problem, or it is a marketing problem. Now, in order to saturate the Newcastle's capacity, which is just saturated at 46%. Yes. It does not mean it is good also, because you have big parts of the capacities that are not saturated. So still is a problem. Although in order to be responsive, and this is something we have to have always in mind, perhaps we should never try to saturate our capacities at 100%, because if we could saturate our capacities at 100%, we will not be able to be responsive. So we should have always idle capacities, perhaps at 15% or so. And this is what the Japanese are with lean management. By the way, they are always having more capacities inside their system than what they require. Why? In order for the system to have some responsiveness. So this comes actually from queuing theory. I don't know whether you know it. So it's like when you are in the checkout. When the operator in the checkout is busy all the time, so it means capacity saturation is 100%, the queues in front of them, so the responsiveness of the checkout will decrease, so the queues will be longer and longer. And when the capacities are not saturated 100%, it means that the operator is, from time to time, is idle. So the flow is much better, right? So it is also like a highway. When the highway is saturated, there will be long waiting times because people will experience bottlenecks. But if the capacity is not saturated 100%, perhaps 70%, 75%, so the traffic will be flowing much better. So this is very important result, by the way. 100% is, yeah, we could have, yeah, in order to take this into account, by the way, we could, yeah, impose here the constraint, let's say, yeah, it should be equal to, let's say, 750, but we did not do this because this is not our objective. The objective is to solve the problem of the transshipment, right? Good. What about having a short break? Let's say 10 minutes of break. We meet again at 11:16. Of course, if you would like to calculate, etc., to spend your break while calculating, you can do it. Now we should continue. Yes, we will now deal with, um, yeah, with an example on supply chain execution, which is related to the theory of constraints. I don't know whether you have done it, but yeah, as I told you, this is not a course on theory of constraints, but we'll just look at it and see how it can help us in supply chain innovation problems. So TO is TOC, or theory of constraints. Who has already had an idea of theory of constraints? Who read the book, The Goal by Goldratt? No? Yeah, perhaps you should. It's an interesting book. And in this book, The Goal, Goldratt is describing the theory of constraints. And he's saying, actually, that we should plan starting from the constraint inside the production system. We will see what the constraint is. Now, TOC helps improve a process performance by identifying and exploiting its bottleneck. What is a bottleneck? What is a bottleneck? Yeah, you see here we have a bottleneck, obviously. Yeah, there will be a bottleneck because we have a broad road, and all of a sudden it will be tight, so there will be a bottleneck. Then, yeah, in manufacturing, when we have different equipment or different machines that are in sequence, which equipment will be the bottleneck, actually? The slowest, yeah, with the lowest capacity, right? So the slowest equipment is our bottleneck. So the pace or throughput rate is determined by the bottleneck, which is the slowest part of the chain. So here, a bit of theory, Goldratt's book. If you want to read it, of course you can do. This is you can have the read as a evening read, so it's a nice book, right, without a lot of equations. So the theory of constraints is about improving the supply chain's throughput, levels of inventory, and operating costs. The key part of this is achieved by focusing on the supply chain's constraint to make sure it is utilized to maximum benefit, buffered with appropriate inventory, and improved with heightened capacity where possible and where such improvements are beneficial. Okay, it may seem a bit too much here, a bit abstract, but we will see how it works. So let's say we have this production system. We have different work centers, one after the other. Work center 1, 2, 3, 4, 5, and 6. And then we have different processing times for each processing for each work center. So for WC1, work center 1, we have 2.5 minutes per unit. So that equipment spends, or the people working in that work center spend 2.5 minutes in order to make 1 unit. In work center 2, 3 minutes per unit, etc. So here, when you look at this, what do you think? What is the bottleneck? What is the bottleneck here in our system? 4, it is work center 3. Why? Absolutely. So it's the slowest one. The slowest one because it is needing or requiring 4 minutes for each unit. So 4 minutes required by work center 3 to make 1 single unit. So now imagine this situation. You have 6 work centers that are in sequence, and then you don't care about the constraint, you don't care about the bottleneck, you are just caring perhaps about the first one. The first one happens to be very, very quick, or you may care about the work center 5. You don't want to say, I don't want to have work center 5 idle. I would like, okay, 1.5 minutes a unit. So I will be just releasing work inside the production system so that I'm saturating some of the equipment here. What would happen in the production process? So there will be a lot of queues. What does it mean having a lot of queues? We will have a lot of work in process inside the production plant. So what you will have perhaps just in front of some equipment, there is nothing, but everywhere else, you would have a lot of equipment, a lot of semi-finished products, or a lot of components, products in queues. And what does it mean when you have queues? It means that the cycle time will increase. So you will have, let's say you are releasing, look, we have in work center 3, we have 4 minutes per unit. It means how many units can we do in 1 hour? 4 minutes per unit. It means 15 units per hour. So it depends always on how many releases in the production system we have. So if we release, let's say, 30 units per hour, what does it mean to release? To release, it means that you are just launching them in the production system. You are releasing. So, and when you release a products in the production system, you start counting the time of their manufacturing time from the moment you put them in the system. So here, you will have queues accumulating in front of the production systems, or in front of the working centers, leading to the fact that the manufacturing cycle times, lead times will increase. And this is something that we don't want to have in the production system. When you go to a manufacturing plant and you see everywhere there are semi-finished products waiting for being processed, This is the worst scenario that you get. Why? Because, and this is, here we have the Japanese system, that you don't know where errors happen. So if you had some error happen, and you have already done a big batch that has some mistakes, you will not discover it, until late, right? Because there has been a lot of time until they have been done. So this is what we would like actually to deal with and to deal with in production, is that we reduce the working process so that we are able to identify errors very quickly, and then also in order to have visibility inside the production process. You don't have also an infinite space inside your production plant, right? So the idea here is that what we should do is that we have to plan, or we have to release products inside the production system based on the capacities of our bottleneck. So our bottleneck can make 15 units per hour, 4 minutes for each unit. So we should not release more than 15 units per hour. Because if we release more than 15 units per hour, what we will have accumulation of work in process in front of each work center. Right? And this is something we don't want to have. So now imagine that we start where we release at 15 units per hour. So at 15 units per hour, what we will have a saturation, 100% saturation of the bottleneck. The bottleneck will be working at saturation, and we would like also to saturate the bottleneck. Why? Because the bottleneck is the most costly one. So the speed of our production system will depend on the work center 3, which is the bottleneck. Now, we saturate it with 15 units per hour by releasing in production, right? So it is called inside in theory of constraints jargon, it's like there is a rope. So the bottleneck is pulling actually how much products we should release into the system. Now, if we are saturating the work center 3, which is the bottleneck, it means that for work center 2, we will be working at 75% utilization rate and 62% utilization rate for work center 1. For work center 4, we are working at 2 divided by 4, which is 50% utilization rates, meaning actually that the capacity per hour is 30 units per hour, but if we do this, we release production or products inside the system at 30 per hour, we will have accumulation of stock. We don't do it, and still WC4 will work at capacity or realized units per hour at 50. So you can see the very, very low row here, the realized units per hour is equal to 50 everywhere, right? But the capacity utilization will differ. So work center 3 is the constraint. It has the lowest capacity of the 6 work centers. It is utilized at 100% of the time. It is the bottleneck resource. So we define here a bit of technical terms. The drum, in theory of constraints, it sets a drum beat for the entire chain, and that drum beat is set by the constraint resource. And this example is 15 units per hour. Believe me, this is what most of the companies do, and you should not do when you start as a supply chain engineer or purchasing engineer, production engineer, whatever. Look, you have a constraint inside the production system, and perhaps some companies say, okay, we would like to accelerate our production. What they do is that they release more work inside the production plant. What does it mean, release? It means, they are launching them at the first work center. Because they believe when I launch more, I release more, things will get faster. But the opposite happens. Because the constraint will do always the same work, it cannot do more. What you will have accumulation of stocks inside your production plant. Whenever you have accumulation of stock, you will have a production time that will increase. And this is what companies do. They release even earlier. If you release earlier, things will get even worse. So we have really to be very careful. Don't release earlier. If you have, you cannot satisfy the manufacturing cycle times, the lead times that you are really targeting. You have to think from this perspective, but never releasing more, because releasing more will induce more and more delays. Okay, because we start always counting the lead time from the moment we release a certain product inside the plant. Yeah, you have to think about it. So the release of a batch or release of a group of products, it is happening at a certain point in time. And you have to choose it. So it is not released like this. There is in the plant, there are people who care about this, when we should release which batches, which goods to be worked on the plant. Then the rope provides a signal to the feed rate into the chain. It means do not launch or pull more than 15 units per hour into the chain. This is very important, right? So it is like a rope that goes directly from a rope that is going here to the feed-in system or to the release system and say to that system, do not release more than or just 15 units per hour, otherwise we will mess up our process here, okay? And then, of course, what you have to think about that the bottleneck is very costly, because if the bottleneck slows down, your entire process will slow down. So your entire output will slow down. So if, let's say, for some reason, here it is not buffered enough in front of the bottleneck, what will happen? It will happen that the bottleneck machine or the bottleneck equipment will be idle. And if it will be idle, this will have a direct implication on your final output. Your final output will go down. Does it make sense? So this is the theory of constraints. And it's extremely important. Do not plan just by looking at, you would like to make, this is the spirit before. I would like to make my production equipment functioning all the time. I don't care about the releases, everything. The machines should be, the people should be somehow busy. But then there will be a big chaos in the production plant. No, we should plan based on the capabilities and the capacities of our bottleneck. And this way, you will have buffers perhaps just here, and buffers at the end, of course, because these are the products that are made, that are finished, they will be buffered there. But then you will not have, theoretically, you will not have anything here before. So this will be a production system with the lowest work in process inventory. So the steps and the TOC, the theory of constraints. So this is the algorithm that has been proposed by Goldratt for the theory of constraints. TOC, as developed by Goldratt, contains an overall SC improvement process. It means, so the algorithm looks like this. First of all, we have to identify the constraint in the production system. Then we have to exploit the constraint. What does it mean? We should look after it, schedule and maintain it well, stuff it with well-trained people, competent people, buffer it with feed inventory. It should not stay idle, because when it is idle, the whole system will slow down. And we should buffer it with feed inventory so that it doesn't stop due to the lack of feed or releases, right? And then subordinate all decisions to steps 1 and 2. What does it mean? It means steps 1 and 2 are the most important ones. Everything else is secondary. So subordinate all decisions to steps 1 and 2. So review all other activities of the process to ensure that they are aligned with and truly support the needs of the constraint. So everything else is secondary as long as our bottleneck is saturated, it is not idle, and functions well. Then what we can think of is to improve our constraint, to elevate the constraint. Undertake actions to improve the constraint's throughput. And therefore here it comes the supply chain innovation part, right? So we would like to innovate our production, our production part in the supply chain. We have to look at the constraint. It means where things perhaps are slowed down. And we may think of elevating that constraint, of extending the capacity of that constraint. If by steps 2 to 4, the constraint has been eliminated. Now, if you eliminate the constraint, before it was workstation 3, you remember? It was the constraint. But if by chance, not by chance, but if after your work, after your improvement, that constraint is not more constraint because it started to be faster, then we have to look at the other workstation that became now the constraint, because the constraint can change. Right? You improve one, you stuff it with more people, you bring a new equipment, and all of a sudden, what you have the constraint that changed. Right? We will see this in an example. Okay, workstation 3, 4 minutes per unit is the constraint resource. So this is the bottleneck with the lowest capacity of the 6 work centers. As such, work center 3 determines the speed of the process. The objective of step 2 in the methodology is to improve the production rate of the bottleneck. For example, by using Clase. This is a continuous improvement from the Japanese system, the lean Japanese system. The company tries to improve the process little by little. Suppose that the processing time in the bottleneck, WC3, is reduced from 4 minutes per unit to 3.5 minutes per unit. Let's imagine this. You can look at your slide. I don't know if you have it already. So what will be the constraint now? Or what will be the bottleneck? Still, the improvement was not so good in a way that we are able to improve the situation. So the objective of step 3 is to adjust the rates of the other work centers in the chain to match the constraining process. Okay, still the constraint, but we are faster. So the constraint, the bottleneck does not produce or does not take 4 minutes per unit. It takes now less than 3.5 minutes per unit. Now, because the work center 3 is still the lowest work center, the whole process should be slowed down so that all work centers take 3.5 units per unit. So we have to orientate all of our production on the bottlenecks. So we have to slow down also the other work centers. And the question is how to slow down the process. It may be for you unimaginable, but it is true. We cannot, when we have a linear production process, we have a bottleneck with a certain capacity, we cannot produce more than what that bottleneck can produce. At the end, if it has 4 units per minute, we can produce 15 per hour, full stop. Even if the others are working full capacity. If they are working full capacity, the others, you will have accumulation of stock. So what should we do? In order to have a good plan, good managed process, we should slow down the other processes because we cannot produce more than 15 per hour. Reallocation, these are the techniques. Reallocate workers from fast workstations to another one, perhaps another workstation in the plant. Modify the number of shifts. Instead of working 3 shifts, perhaps you are working just 2. I mean here for the work centers that are fast, or just bringing the production rate down. If it is an automatic machine, instead of making, 30 units per hour, you are just setting it to make 20 units per hour or so. So the objective of step 4 is to revise and invest in addition in additional equipment or new technology whenever it is possible. So we have work center 3. Yeah, we try to make it faster somehow. Now, let's imagine once the processing time at WC3 reaches less than 3 minutes per unit, now we have new constraints. So we keep improving our constraint in a way that this work center is not the slowest anymore, and this will lead to other work centers becoming the new constraints. And we are redoing it again. You see how the algorithm is working? So always look at the slowest part, then of course you have to stuff it well, etc., etc. Try to improve it, and keep improving it. And once you improve it, other work centers are becoming the new constraint, or other work centers become, and then you keep doing the same thing. And in this way, we are improving all the time. And keep in mind, you cannot produce more than what your constraint in the production plan or the production system can produce. You cannot. I have an exercise for you, a short one. This exercise, by the way, I posed it once in an exam. So it is 1-to-1. I got it from the exam. I put it here on the slide. And you will see it's a simple one. You have just to understand what the theory of constraint is. So a company manages a small factory that produces toy cars involving 4 main steps. Cutting raw materials of car parts, assembling the cut parts into a toy car, painting the assembled toy car, and packaging the toy cars for shipment. So very, very simple process with 4 steps. Then details of each step. We have the cutting, can process 20 toy cars per hour, assembly 15 toy cars per hour, painting can process 10 toy cars per hour, and packaging 25 cars per hour. We have the current production. Each toy car needs to go through each stage of the production process, and the factory operates for 8 hours a day, so for 1 shift. So now, the questions. Identify the bottleneck in the process. Identify the bottleneck in the process. I need an answer very quickly. Which? Painting. Painting is the bottleneck. Why it is the bottleneck? Because it's the slowest one. It makes only 10 toy cars per hour. Calculate the current output. No. The current output. The output. I'm not saying the rate, I'm saying the output. It is 15 multiplied with 8, which is 120. 120 per day. Okay? So this is, yes. I'm sorry. It's 10 multiplied with 8. 80, I'm sorry. Good, so bottleneck. Is painting. Then we have 10 units per hour. The output is 10 multiplied with 8, it is 80 per day. Okay, now propose solutions to maximize the number of toy cars produced per day. So these are the actions taken to double the output of the current bottleneck. And this is the innovation. This is the improvement. This is what I would like you to do. how could you improve the process in a way that you may double? So perhaps you may double, improve, or triple, whatever. You may double here the current bottleneck. What are the possible solutions? So we have here, look, we have cutting, assembly, cutting, assembly, painting, and packaging. Right? Okay, so this is our process. So how could we double the output? Obviously, we have to tackle the bottleneck, right? So what does it mean? It means that we create perhaps another painting station. Yes. So it means that we'll have painting 1 and we'll have a painting 2. Right? So we are creating one in parallel. So we don't know about the process, how it works exactly, whether there are people painting it or it is like, yeah, if it is in the automotive industry here, we're talking about toy cars. In the automotive industry, it is a completely automatic process. People are not intervening in it at all. Okay, well, what could we do also? Just thinking. We can perhaps use a paint that can dry faster. Why not? Paint that dries faster. So, yeah, here this is about, yeah, how to innovate, how to improve the process in a way to make its output higher by focusing on the constraint. Now, let's imagine we are doubling the output of the current bottleneck. We are doubling the output of the current bottleneck. What does it mean when we double it? It means that all of a sudden we have a painting process that can do 20 toy cars per hour, right? So doubling the output, meaning that we have 20. So new output painting is equal to, if we double it, it is equal to 20 units per hour. When it is 20 units per hour, is it still the bottleneck? No, it is not the bottleneck. Which step will be the bottleneck now? The assembly, 15. And what would be the new improved output of the entire process? 120, exactly. So the new output of the entire process is equal to 15 multiplied with 8 equal to 120. So, and this is how the theory of constraints work. Okay, so how to apply the algorithm of TOC. Any questions on this? How did we? It is by multiplying, because we are operating an 8-hour shift, and then we are producing, okay, before the improvement, we are producing at the bottleneck 10 per hour. So 10 multiplied with 8, it will be 80. Yeah, because before it was on the assembly. So yeah, sorry, before it was in the painting, and then we doubled the new output of painting. It was 20. Now the bottleneck changed, and the bottleneck now is the assembly, which is 15 multiplied by 8, it will be 120. Any other question? No? Okay. So yeah, we have 10 minutes to finish the last example. So we have done strategic aspects of supply chain, how we could deal with them with analytics. Then we did the design, supply chain design problem. Yeah, the simulation and the simplex, the transportation problem. Then for the execution, we have done the transshipment problem and the TOC. So every time we're changing the process, we're changing the structure of the supply chain, the design of the supply chain. And at the end, yeah, we will look at people in the science, in the supply chain. And we will see a problem where we can use analytics actually in order to solve it. So a problem related to people. So here you have the solution. So okay, so supply chain, people, processes. We will talk about leadership. Yeah, leadership is a challenge, be it public or private organizations. Quality of leadership is critical. So especially what are the kind of competencies that you require for supply chain managers? I think this is an important question. Leadership quality today is very variable. And is it possible to apply analytics to any leadership dimension? And the idea is yes. Here we have the concrete problem. A company wishes to develop a leadership appraisal system that can be used to assess both new hires and incumbent SC leaders. What is appraisal system? It's like assessment, evaluation. Yeah, you would like to hire a new supply manager. You would like to know whether the candidates are good enough for the job or not. Or you would like also perhaps to evaluate the adequacy, the appropriateness of the supply chain managers that you have, the existing ones, for the job. A small project team is formed in order to progress with the initiative. After considerable study and consultation, the project team identified both the performance index to use and key leadership accidents. Okay. Now, yeah, you defined a performance index. The performance index is an aggregate index that is based on delivery performance, order lead time, flexibility, costs, and days of inventory. You see how important days of inventory are here? So inventory. So the lower the inventory, the better. The shorter the delivery time, the better. The higher the service level, the better. So anyway, so this consulting company has defined these characteristics to assess or to appraise the performance of a supply chain manager. So you are a supply chain manager, they will be looking at your department, to which extent you are delivering on time, to which extent your costs are under control, etc., etc. And then they use the score system, so like weighting all of these characteristics. And then they start with 100. Yeah, we don't know the exact calculations, but at the end, what they found for leader 1 is a score of 88. So this is the performance. The performance is 88. Yeah, we have 9 leaders. Performance is of the second is 68. Yeah, somehow lower. You can see 7 is 51, much lower than the others, etc. And then we have here some features. some features of the person, a profile of the supply chain manager. So we are trying to find more or less correlations between the performance of leaders and certain features of these persons, whether they are responsible adults. Yeah, because the responsibility is very important. Some leaders, for example, they care about their employees. Yeah, leading and managing is about caring also, about care about people. If you are not responsible, perhaps you will not be a good leader. Then, whether they are trustworthy or not, then whether they are qualified and experienced. So here, this is from 1 to 10, let's say, values that have been attributed, dedicated to each of these leaders. Whether they are political or not, risk aversion, whether they are risk averse or not, and self-interested, whether they are interested in improving, etc. So now, what can be done? What can be done when you have a certain number of characteristics of a profile of a job role, and then on the other hand, you have the performance of the people? What can you do? What can be done here? So this is the typical example for a regression analysis. Should do a regression. So it's what is the dependent variable? The dependent variable. What is the dependent? It is the y. Right? The dependent variable. So the dependent variable the y is the performance index, right? And I would like to understand to which extent this performance index, so it is a function, regression analysis to be a linear function of all the other attributes, responsible adult. Trustworthiness, risk aversion, etc. So all of these variables. I would like to understand whether really the performance index depends on these variables. So I will do a regression analysis, and I will see whether the regression results are significant or not. So, and what are the variables perhaps that are, so these are called the independent variables. Which ones are significant and not, and which ones are not? Who has never done a regression analysis before? Who has never done it? So it is not a problem. So I will show you how it is done, and it's done very quickly with Excel. Who has done already? Okay, so this is very interesting. There's people who did it and did not do it. Yes. So it's very interesting. Always, every year the same. I would like to solve this paradox. Right? But, yeah. Perhaps at some point in time I will. Anyway, it's just for kidding. Huh? Let's go to our example. And then here you have to install and add in, right? Also, so this, because the solver will not help you here. The solver will not do the job. So again, you have to go to File, Options, do the same procedure as before, add-ins, and then you have to install the Analysis Toolpath. This is the one. I have it already installed, but you have to install it. So the ones that are using a lot of statistics in their work, yeah. Analysis in Italian. I think it is strumentary analysis. I think so. Yeah, because yeah. Yes. So analysis tool pack. Yeah, you see, it is. I did not install it here with ABB, so you should install this one. Did you install it? Done? Who did not install the analysis tool pack? Who installed it already? Okay, they're still here. I have to say. Anyway. Okay. Now, then I go to data, and then you should find data analysis there. Yeah, it is just below the solver. You will find data analysis. Right? And then what we will do is to click on data analysis. Click on data analysis. And then you will have a menu of many statistical tools. And then you choose regression. So once you click on regression, you will find this. Did you get already this window? No? Yes? Okay. Now we have to enter the inputs into the regression analysis. So what is our dependent variable? Dependent variable is the performance index. So the performance index will depend on certain profiles of the people. So here I click on the input Y range. And by the way, I will get also the title of the column also with it. I will tell you why. So the input range is from B1 to B10. So this is done automatically by Excel. And then I will define the X range, which are the independent variables, responsible adults, trustworthiness, quality, experience, etc. And then I will also integrate the titles of the columns also inside, right? So I'm getting the entire table, and Excel has already put that, inserted that in the input X range. And then here I have to check labels. When I check labels, it means that the first row is the title. So Excel will say, okay, we'll understand it. Okay, it is not something that I have to introduce into the calculations. It is just for knowing what are the titles of the different columns. And then I have to tell Excel, okay, I would like, okay, the others, you should not do anything. I would like to get the result, let's say, in the output range. So what I would like to have the result here. So I will click on the output range. I don't know what happened. Yes. And then I will say I would like that you insert the results here in that J19. Just insert the results there. And then I will press OK. And look what Excel does for me. The entire regression, all the calculations. Did you get this? Did you get the results? Hmm? No, not the entire table. Please open the data analysis. Yes, regression. Yeah, you can Google it. What is regression exactly in Italian? Okay, regression, and then yeah, and then you include the labels, and then you have to check labels. Welcome. Good. Yeah, what is the first thing you have? In general, when you have this kind of results, there are a lot, right? Yeah, you may ask yourself, how should I read this table? Now, in order to read the table, so I'll make it a bit bigger, and then not in gray. Yeah, we will finish with this, and then should be done. Okay. So, first of all, I have to look at the significance. Significance F. So whether the model is significant or not. And then if it is lower than 0.05, which is 5%, I can assume that the model is okay. I can say the model is significant. Okay. Now we have here 0.001, which is 1 per thousand, which is much lower than 5%. I can see that my results they are significant. And yeah, you know, because there is hypothesis testing. I don't want to get into this, but the H0 and H1. So H0 is that all the coefficients of the regression analysis they're equal to 0. But here, when we have significance that is good enough, we can assume that they are not. So that the null hypothesis is that the coefficients of the regression analysis they are different. So this is what we are showing. So this is H1, right? This is related to hypothesis testing. I don't want to get a lot into it because this is not a statistical course. Just to tell you that here, is significant. So we can trust we can rely on the results of the regression. First of thing, so looking at that. Second thing, I would like that you look directly on the R squared or the adjusted R squared, and better the adjusted R squared. The adjusted R squared. In the adjusted R squared, it should be greater than 0.8. And then here, we have an adjusted R squared that is 99.85%. Meaning that, what does it mean? It means that the independent variables, they explain well our dependent variable. So when we have this, the independent variable, we can predict very well our performance index. And this is a very relevant result. So knowing the features of somebody, you can predict its performance. And therefore, regression analysis is one of the tools of AI, because what AI does predictions, and regression analysis can do also predictions. Right? You can predict whether a new hire is good enough or not by looking at certain characteristics, because you have the data, you can do the regression analysis, and you can predict his or her performance. This is the same result here. Okay, adjusted R squared is good. Independent variables are explaining the dependent variable. We have significance, and then I have to look at the p-values here for the different variables, responsible, adult, trustworthy, qualified. You see why I'm putting them inside the analysis before? I'm putting it because then Excel will show me exactly the labels, right? Here, the labels are found again here. And then I have here the coefficients, right? And then I look at the p-values. For example, I told you, if it is smaller than 0.05, there's significance. So for the intercept, okay, responsible adult is 40%. No. So responsible adult is not here, it's not significant. Trustworthy is significant. Qualified is significant, 0.08. Political is also significant. Risk averse is not significant. It's 0.21. It's much bigger than 0.05. And self-interested is also significant. So just to wrap this up very, very short, I will go back to the slides. So we do our regression, and then we have here the results that we see. Okay, based on the regression analysis, actually we can, the performance index is 24.7. So this is the intercept, yeah, 24.7. This is the intercept. When you have y equal ax plus b, the term, this is the intercept. Intercept, you get it when you equal x to 0, right? So this is the intercept. And then you have 0.68 multiplied with the responsible other. You find them if you look at the table, 0.6. So the first one, yeah, I don't have it here. Okay, do it very quickly. Yes. So these are the numbers, the coefficients, okay? So you find them the 24.6, 0.68 multiplied with responsible adult, and 3.8 multiplied with trustworthiness, etc., etc. Because the p-values for responsible adult and risk aversion are greater than 5%, the project team considers removing these variables from the analysis. So they are not significant. So they are not explaining very well. We can say that they are not contributing to the explanation, perhaps, of the performance index. And therefore, we may envisage removing them. But on review, the chair points out, the results presented are based on one survey of 9 leaders only. We should think about this. So the data that we have, it is based on only on 9 leaders. Perhaps we have to extend our sample and then recalculate everything again. The ratings for the independent variable risk aversion, we found that the independent variable risk aversion is not significant, right? It was, I don't know, 0.21 or so, which is bigger than 0.05. But they are very bunched with 5 out of the 9 leaders rated as 4. So the question is risk aversion good or bad? So if risk aversion, it means disliking risk. So do you think that managers should be risk averse or should be risk, they have a certain level of risk affinity? Actually, when there are some studies showing that being on one of the extremes is bad. So if you are very risk averse, it's bad because you are not taking risks. When you don't take risks, you don't do anything. And if you like too much risks, and they are just launching in every project that is even very risky, this is also very bad. So actually the performance may go like this. So risk here, high risk aversion, and here risk affinity, right? So having from 1 to 10 risk aversion, it means that the more risk averse, the better. So we have a problem here in the regression. The regression, it doesn't work. It is not like the more the better. We have to be very careful. Because in the regression we are saying, yeah, the more of X, I mean, the more risk aversion, the higher the performance. It's not true. So the change suggested perhaps that risk averse variable may not be linear. And if it is not linear, we cannot integrate it in a in a regression analysis. That is, high risk averse scores takes no risks, are just as detrimental to performance as low risk averse scores. The chair also suggests that the two independent variables in question may be revisited in order to verify the accuracy, the veracity of the rating process, and also to determine the nature of any relationship between the two variables and the performance index. So it could be a relationship linear or parabolic, like the one I draw here. So, yeah, you see, sometimes you get results from regression analysis, but be very critical in front of these results. Do not accept them directly, okay? Try to think about them better, about your variables, etc. And then, yeah, you can do some experiments, remove some variables, try to think more about your variables, about how you assess them, whether they have linear, there are linear parabolic relationships that it is here. But take it as a first step to do much more work. Do not just take the results and believe in them directly, okay? Good. We finished this. Do you have any questions? By the way, I prepared another exercise. I told myself if we go very fast through the exercises, still we can do it. But we will not have time to do it. What I will do is that I will upload it. And if you are interested in doing it, try to do it. Okay? So, and then if you have questions about it, you can ask me next lecture. But it is just up to you. If you'd like to exercise more, you can do it. Okay, thank you very much for your attention. Thank you for remaining a bit longer. Today it was important that we finish the data analytics part. Thank you and see you next week.